Hello.
Hello, good evening, sir. Sorry I'm
Yeah.
late.
Good evening. Yeah. So you can hear me, right?
Yeah,
Okay. You got the two organic books.
yeah, I got them.
You downloaded it.
Yeah,
So, so one of them is the textbook, which is the organic chemistry book by McMurray, and the next thing is the solution manual, right?
yeah,
So what you need to do there is don't worry about what is happening in your Allen and how they are teaching in Allen. See, the way they teach organic chemistry in India, at least in any coaching institute, you will find the way is really bad. Why do I say it is really bad? Because you will realize that have they done a chapter called GOC for you?
yeah,
They have done that chapter, right?
hmm,
General Organic Chemistry.
yeah, that,
So basically, what they will do is everything, so many effects, so many things they will pack into one chapter. And this chapter is going to be super important and it is going to be used. Concepts in this chapter are going to be used throughout the rest of the chapters, right? You
yeah,
have seen they have taught you many effects and stuff like that, right?
yeah, mesomeric effect, inductive effect.
Yeah, yeah.
Yeah,
So many things they will teach you at one shot, and it is difficult to remember for the student, and it becomes like a confusing thing. Okay. So then after that, they will start with hydrocarbons and then they will start with different functional groups and so on, right?
yeah,
So this becomes confusing, especially if you don't have that much time. It is difficult to do everything well like this. So what I would recommend is you follow this book. You see the contents of this book, the way it has been explained. You will have like in the beginning, there are chapters like, for example, if you look at the first chapter, it is structure and bonding, right?
yeah,
Structure and bonding will talk about all of the atomic structure, hybrid orbitals, how bonding happens in covalent compounds, and so on. Then you have polar covalent bonds, acids and bases. And then slowly he teaches everything. Third chapter is about alkanes and their stereochemistry, right?
yeah,
So the point is that organic chemistry is a big subject. You cannot cram everything in one chapter and hope that the student is okay with it later. Okay. So what you will learn in this book, and if you follow this book properly, is an organized way to learn the subject, which is slow and gradual. Okay.
okay,
So when a particular effect is important, it will come and it will be taught at that stage, not in one chapter in the beginning of the course. Do you understand what I'm saying?
yeah,
All of the GOC effects and everything that you have seen in coaching, like all of that will be covered here, but it will be covered in the right place when there is a reaction that you need to understand which uses that. Okay. So what you need to do is follow this book properly. You can like go in a sequence and not worry about anything. Like you can go in a sequence from chapter 1 till almost like your syllabus will be around chapter 24, 25. The only thing you can skip
oh,
there are chapter 12 and 13. Do you understand what I'm saying? Chapter 1 to
yeah,
chapter
yeah. I was just
25,
downloading it
uh, except chapter 12 and 13.
because,
So you can download, you can open the textbook. 12 and 13 will be the spectroscopy chapters. Okay. So this is not in our syllabus, nuclear
okay,
NMR spectroscopy and all infrared spectroscopy. This is not in the syllabus. But everything else, chapter 1 to chapter 25, you should go in the sequence that has been shared in the book. Okay. Also,
okay. I'll like do the questions rather.
that's why I've sent the solution manual because many of the questions will be solved there. So that will help you check whether you're understanding or not. But it will not help you if you just look at the solution directly, right? So make sure that you do
Yeah,
the
yeah,
questions and try it yourself a little bit, and then you can see the solutions, right? Do you understand what I'm
yeah,
saying? If you follow this sequence
Yeah,
properly,
got it.
all your concepts will be sorted. And in the beginning, it might be feeling weird to you because Alan is doing something more and they have already gone ahead and stuff. But slowly over time, you will catch up. Okay. Over
Okay.
time, you will catch up. And if you read this book second after doing Alan, like it will be a revision, and then you will really understand if there are some gaps in what they taught in Alan, then you will get to know here when you do it. Okay. So make sure that you follow the sequence. Don't skip anything. Don't think that, okay, I can skip this chapter and it will be fine. Organic is a difficult subject if you try to skip things. Okay.
Okay.
So everything in organic is connected to everything you have learned before. It builds on top of each other, right? So it's like that. So you cannot have gaps in your knowledge. That's why you need to follow the book carefully. And 1 year is plenty of time. Like from now till December, you have time till December. So March till December, right?
Yeah, 10 months.
This is plenty of time to finish these chapters. You also have the solution book. You have to just go through the book and try to understand the concepts. It's all about understanding that concept. Whatever they are doing in Allen, you can use this book to support it. Do you understand what I'm saying?
Okay.
For example, suppose they are teaching in Allen alkanes and all, and they are teaching reactions like SN1, SN2 reactions. Okay. They will be teaching many different reactions and reaction mechanisms in Allen soon. So if you are getting stuck in your coaching class, what they are explaining, you should go to that relevant chapter, relevant section and read from here. Okay.
Uh,
But don't
okay.
think that you can just figure out everything if you just read relevant chapters from here. Ideally, you should have your own parallel plan where you are slowly progressing in the book. Okay.
Okay, so right now I'll just start reading from the beginning, like atomic
Yes.
structures.
Chapter 1 say, chapter 1 is not atomic structure. Chapter 1
Mm,
is structure and bonding. It's not just atomic structure. It has all of the stuff at atomic structure plus hybridization and covalent bonding, right?
that is the, yeah.
So you should start from there because obviously that's the fundamental. From there only you can understand everything. Okay. So
Oh,
what I would say is right now our class is going on in Alan.
no, not right now.
Okay. So the 12th grade classes have not yet begun, right?
No, I'll start in March.
Okay, fine. So you have some time. So what you should do is daily you should allot, daily you should give 1 hour for organic at least for
Okay.
now. Because if you give 1 hour for organic right now, you will find it very easy to progress through chapters 1, 2, 3, so on. It will not be very difficult in the beginning because you have already covered it a little bit, right? Already.
Yeah.
So you will be able to progress and you will be able to, hopefully, by the time they start teaching in Allen, you will already be on chapter 5 or chapter 6, which is alkane, alkene, and all reactions, right? So
Yeah, that's,
see, chapter 5 is stereochemistry of tetrahedral centers. It's a very important idea because he teaches you the R and S structures and how isomers are formed and all, stereoisomers, right?
yeah.
Chapter 6 is an overview of organic reactions, which is like basic fundamentals, how to understand organic reactions. And alkene, alkane are 7 and 8, right? Chapter 7,
Hmm.
chapter 8. So
Yeah.
7, 8, 9 actually are alkenes and alkynes reactions. So actually in your class, you have already covered everything till 9, I think,
Yeah. Like
right?
hydrocarbons.
But they would have
Hmm.
done it in a very fast way or very weird way they teach. So you should do it in a proper sequence. If you do it in the sequence, no, go one by one, then you will truly understand everything. Okay.
Okay.
So your target should be ki by the time the Alan starts stuff, you should reach chapter 7, 8 and all. You should be near here,
All right.
right? And once it starts, once Allen classes start, maybe they will start with haloalkanes and alkyl halides and all. So then once the classes start, then your job would be to follow the classes carefully, what are happening in coaching, and immediately read the relevant sections from Murphy. Do you understand what I'm saying?
along with like all the other topics also.
So if the chapter that is going on in Allen is, let's say, they are doing alkyl halides, you can see that that is covered in chapter 10 and 11, right? So if a class happens on alkyl
हाँ
halides, you should go to chapter 10 and 11 and try to finish that while the classes are going on in Allen, right? Do you understand what I'm saying?
okay हाँ
And if you are getting some
yeah
free time, then you have to progress along with your normal progression, right? Normal progression is from the beginning what you are doing, right? So basically, it's a
yeah
matter of balancing. Ultimately, your target is you have to reach chapter 25 by the end of the year, right? That's the target. Okay.
yeah
And
but there
if
are like
you,
30 chapters.
th there are 30 chapters, but some of them will be beyond our syllabus. Chapter 25, I'm saying, is biomolecules, carbohydrates. So chapter 26 is biomolecules, amino acids, peptides, and proteins, right? So
Yeah
our job is to reach till chapter 25, 26. That depends on the exact syllabus that is there in NCERT, but everything before that is definitely in the syllabus. Do you understand what I'm saying?
अच्छा हाँ yeah
तो लगभग 25, 26 तक पहुंचना है, right? And you have to reach there by the November, December. And when I say you have
yeah
to reach there, if you are able to reach there having solved everything in the McMurray book, having tried all the questions in the McMurray exercises, having looked through the solutions, understanding what is going on, then automatically your organic will be super strong. कुछ दिक्कत नहीं होगी फिर. समझ रहे हो?
हाँ ठीक है
It is possible to self-study and become very strong in organic, but the problem that students face, why they are not able to do it, is because first of all, they are not reading from a proper place. If you are reading coaching module, there is no chance you will become super strong. Coaching module is like a collection of information. वो माइंड में फिट नहीं होता है सही से. समझ रहे हो मैं क्या बोल रहा हूँ?
हाँ वो बहुत अजीब से लिखा रहता है
हाँ, मतलब एक ही जगह बहुत सारे चीज अगर तुम मिक्स कर दोगे, सब हौज पौज हो जाएगा माइंड में. इट विल नॉट बी लाइक अ नाइस framework in your head. The way the book is designed, if you go slowly one by one, everything will make sense. ठीक है?
हाँ
But
ठीक है
it will not make sense if you rush through the book without doing exercises. समझ रहे हो?
हाँ
तो वो,
एक्सरसाइजेस करना
हाँ, एक्सरसाइजेस कर करके सॉल्यूशन चेक करके देन ओनली यू शुड प्रोसीड अहेड, बिकॉज तब
हाँ
यू विल नो फॉर श्योर कि समझ में आ रहा है, एवरीथिंग इज फाइन सो फार. The
ओके
point is to balance your time nicely so that Allen classes, whatever is happening, you can support that with this book and read the content of this book nicely while Allen classes are going on. They will cover one chapter in 2 weeks or 3 weeks. By then, you should finish the McMurray chapters also, the relevant chapters. Do you understand?
ओके या
If you follow the process, organic is going to be sorted. There is going to be no issue. Like I have taught someone before who came to me in 12th grade. 12th grade summer ke aspas we started classes. And I didn't even teach him organic. I just told him, follow this book, do the solutions, solution manual, use it, do all the exercises. In 3, 4 months, he was totally awesome at organic. मैंने कुछ पढ़ाया भी नहीं था. मैं तो बस उसको सपोर्ट ही कर रहा था. I was teaching maths and physics. So he became super awesome in organic because he followed the book. You just need to follow it, okay? And there is plenty of
ओके
time. There is enough time to become good at it. ठीक है? Think of your Allen classes as a supplementary.
हाँ
Ki Allen classes will help you like get the exam pattern of questions and give you extra help. But your main way to learn organic should be this book. Do you understand what I'm saying?
okay.
So follow that process.
Yeah.
I will not be able to teach you much because I have forgotten almost everything. अगर तुमको organic पढ़ने की जरूरत हो रही हो तो you will have to give me some slide a week or two in advance so that I can read up. But I will not be able to help you so much directly in organic, but in physical and inorganic, we can discuss everything and fix that. But it is possible for you to self-study and become good at it if you follow the book एकदम sincerely. Do you understand?
हाँ
Think
ठीक
of
है.
yourself as a small child. If you give a small child something to do, like ninth grade, eighth grade, if you're supposed to learn something, you would learn from the beginning. No, you would read in a sequence properly, right?
हाँ.
Because you don't know anything else. That's how you are supposed to read it.
Okay.
So just do that and you will see the benefit in 2, 3 months only. You will see how different it feels. It will feel better. Okay. Okay. We will continue with
Okay.
atomic structure.
Like somewhere में आप
Hmm. Wait, your voice is not very clear. Tell me what you're saying.
a lot of time, many years.
Wait, you have to repeat what you're saying. Your mic is not very audible or something.
Okay.
What are you saying? Tell me.
I was saying that in summer my school gets over for like a month, and
Hmm.
it's only my coaching.
Hmm.
So it's only like half day coaching and then I'm free. So then I can like,
Right. Right. So you have to make your own plan and you have to make it such a way that you should have plenty of time to finish the book by November, December types. Before that, it should be done. So you have to think of it like that. You don't have to rush it. There is no way to rush organic and become good at it. Okay. So because your mind will take its own time to learn these new things. It's like learning a new language. It will take some time to fit in your head. You understand what I'm saying?
yeah.
The best way to do it is to do it at the natural pace and do all the exercises. Then you will know whether you truly know it or not.
Hmm.
Check the
Okay.
exercises, use the solution book, and then do it like that. And ideally, you should take a printout of the textbook, maybe some chapters, and then use a printout physical copy से पढ़ोगे तो अच्छा हो. समझ रहे हो ना?
हाँ ठीक है.
You can keep the solution book online, but use a physical copy for the book. Just take a printout and all.
हाँ ठीक है.
That will be more convenient to study.
Hmm.
Okay, let's get back to atomic structure. So, in the last class, we discussed the derivations in Bohr's model, right?
Yeah.
So, Bohr's model we saw was based on this idea that this was the centrifugal attraction between the nucleus and the electron, and that is equal to mv squared by r, right?
Yeah.
Because of circular motion. This was the first idea. This idea, by the way, Rutherford also had, but he didn't have the second idea which Bohr had, which said that not all radiuses are allowed, not all orbitals are allowed, right?
Yeah. That
Only
integral one.
orbitals, where the angular momentum of the electron is n times h by 2 pi, right?
Yeah.
Only those orbitals are allowed. And using this and using this, these two equations, it is pretty easy to find the velocity in terms of all the other variables, right?
Yeah.
The velocity of the electron after simplifying comes out to be some constants into z by n. And when we write the values of the constant, it becomes like this: meter per second into z by n, right? Correct?
Yeah. हाँ.
Obviously, you can simplify it and get the exact value, but it is going to come out like this. And then we can find the radius also. Radius comes out to be 0.529 angstrom into n square by z, right?
Yeah.
And then energy of the whole atom will be the sum of the kinetic energy of the electron plus the potential energy of the whole system. So this is total energy. It will be kinetic energy plus potential energy, right?
Hmm.
And the potential energy actually is minus 2 times the kinetic energy.
Yeah.
The potential energy of any situation where there are charges is usually k q1 q2 by r. Okay. So in this case, the charges are Q1 is ZE and Q2 is minus E, right?
Yeah.
So the total potential energy becomes KZE square by R negative.
Uh,
You understand what I'm saying?
yeah.
And the kinetic energy is simply half mv square, right? Here me is the mass of an electron, right?
Yeah. Hmm.
So when you do the calculations, because we know the velocity expression, you will see that kinetic energy, whatever expression comes, is similar to the potential energy expression, which comes from here, right?
Yeah. Hmm.
And we saw it last class that potential energy is minus 2 times kinetic energy, right?
Yeah.
And this becomes basically total energy becomes negative of kinetic energy, right?
Yeah.
And it becomes equal to minus 13.6, I think, electron volt into Z square by N square.
Uh,
Something like this will come after you put in the values of each constant, right?
yeah.
Notice that it makes sense because velocity is proportional to Z by N, so energy should be proportional to velocity square,
Hmm.
right?
Yeah.
And this becomes the energy of a hydrogen-like atom. So Bohr's model, every prediction of Bohr's model was valid only for hydrogen-like atoms. So what do I mean by hydrogen-like atoms? What I mean is that it should have one electron.
Yeah.
Okay. So Bohr's model has a lot of limitations. First limitation is this, that it only works on monoelectronic species. Monoelectronic species, which means they should have a single electron. So it can work on hydrogen atom. You can make predictions of hydrogen atom based on it. It can work on helium plus or lithium 2 plus and so on. Do you
Yeah.
understand what I'm saying?
Yeah.
Helium technically has two electrons. If you lose one of them, then helium plus, the properties of that you can predict using Bohr's model.
Uh,
Okay. Lithium 2 plus also you can predict. So the benefit of Bohr's model is that it gives you the energy of an atom. No? It was minus 13.6 Z square by N square, right? This is the
yeah.
total energy of an atom when an electron is in a particular shell. So, for example, if we talk about the hydrogen atom, and if the electron is in the first shell, you will say minus 13.6 1 square by 1 square, right?
Yeah.
But if the atom was in the third shell, you would say minus 13.6 1 square by 3 square, right?
Hmm. Yeah.
So notice that the energy is becoming, this is more energy than this, right? Because it is less negative.
Uh,
The quantity, the magnitude is becoming smaller, but it is all negative, so it is a smaller negative, right?
yeah.
So technically this has more energy than this, right?
Yeah.
So the first n is equal to one shell that has the lowest energy, right?
Yeah.
And as you go higher shells, the energy is more and more, right?
Yeah.
Similarly, if I had to do it for lithium 2 plus, I can do it for lithium 2 plus. The energy depends on the shell in which the electron is. And here Z square, I will write 9, right?
Yeah. Because three atom.
Atomic number of lithium is 3. So therefore, you have to write 9 by N square, right?
Uh,
So Bohr's model will give you the total energy of these types of atoms. Now, why was that important and why was this model so successful? Is because it was able to predict the atomic spectra, right? It was able to
yeah.
explain the relationships that people got in atomic spectra. Now, what is this atomic emission and absorption spectrum? So, the idea was simple. So, since the 1870s and 1880s, chemists had been seeing some weird properties. So, for example, if they took a piece of sodium, for example, right? If they heated this sodium, then the sodium got a lot of energy and later it started glowing, right?
Uh,
if you heat any metal or something, it will start glowing and will glow with a particular color and stuff, right?
Yeah.
So suppose they heated a piece of sodium and it was glowing and releasing a lot of electromagnetic radiation. When they measured the wavelengths of these electromagnetic waves, right? What they discovered was that it was not at all like the radiation that came from the sun, like the typical usual light that we see. What is what is special about the usual light that you see, electromagnetic radiations that come from the sun?
It's a continuous spectrum of light.
Right. It is continuous spectrum. Basically, any wavelength that you can think of, it covers every wavelength, right? So
Huh.
basically, it has all the visible light, all of those wavelengths. It also has ultraviolet rays and X-rays and all, which are smaller wavelengths. It also has radio waves and there is one more infrared waves, which are larger wavelength, right? So
Hmm.
basically, the whole atomic spectrum is covered, like all sorts of radiations are coming from here. So there is UV, X-rays, gamma rays on this side, and there is infrared, there is radio waves on this side. So these are long wavelengths, these are short wavelengths, right? And somewhere here, 300 to 900 nanometer is our visible light. Do you understand what I'm saying?
Yeah.
This is the only light that we can see with our eyes, but actually so many other wavelengths are also coming, right? So
Yeah.
when you see the radiation coming from the sun, it is a continuous radiation. But when you see the radiation that this sodium was emitting, it was only giving some special wavelengths. Special wavelengths were coming out. Do you understand what I'm saying?
Yeah.
It was not at all continuous. For example, it might have been giving 456 nanometer, then 612 nanometer, then 13 nanometer. I'm just making up some numbers. But if it is giving 456, you will realize that there is no 457, 458, nothing. Do you understand what I'm saying?
Yeah.
So when you measured the sodium's wavelength that was coming out or that was being emitted, the spectrum was only a few lines, a few wavelengths, not all of them, right?
Yeah.
So people did this sort of experiment for different metals, and every metal had its own unique emission spectrum. This set of lines that you are getting when an atom is excited and a piece of metal is excited and it emits wavelengths is known as the emission spectrum of that element, right? So
Huh.
basically, in my example, I would say emission spectrum of sodium consists of these three lines: 456, 612, 813, and whatever else, right? Correct?
Yeah.
Now, what people saw was several strange things. For example, they saw that all the time different elements always had different spectrum. Do you understand what I'm saying?
Huh.
Like the frequencies that appear for potassium are always these frequencies and nothing else. Frequencies that appear for or wavelengths that appear for sodium are always these and nothing else, and so on, right?
Huh.
So basically, this was very good information because this became like a sort of a emission and absorption fingerprint. This emission and absorption spectrum became like a chemical fingerprint for that atom, right?
Huh. It was unique to every element.
So now what you can do is you can use that. If you made a table containing all the lines that come from each element, then you can use it to identify unknown substances, right? For
Hmm.
example, if you get a piece of rock and you want to know its composition, the way you can do it is just take a small sample of the rock, heat it, make it glow, and then measure the wavelengths of the radiation that came out, right?
Huh.
if you measure the wavelengths of that radiation that came out, you might be seeing, okay, there is this line is there, there is this line there. That tells you that sodium must be there or calcium must be there.
Uh,
Do you understand?
yeah.
So basically, you have a big table for every element, you know which lines appear in whose spectrum. And then you can identify any unknown substance, right?
Yeah.
So that is a very useful tool for chemists. But the problem is that this is all very good for practical purposes, but nobody knows why these lines are coming. Why only 458 and not 457, right?
Uh,
And why always potassium's lines are different wavelength than sodium's lines? Do you understand?
mm,
And always, no matter where you take sodium from, it will give the same lines. Why always like that? There are so many questions that are unanswered here, right?
uh,
So these questions, like a little bit of it was answered because one guy found the formula that 1 by lambda is equal to some constant. This is uh, Balmer's constant and divided by 1 by 2 square and minus 1 by n square, where n has to be 3, 4, 5, 6.
uh,
This formula was discovered purely experimentally. Like looking at the data, they figured out all the wavelengths are fitting this formula, right?
this is just for hydrogen-like species again, right?
No,
This
this
formula.
was for all elements they found. And these types of
Oh,
formulas were there for different elements, okay? Not just for hydrogen-like species. Okay.
so this one is for hydrogen-like, and then like other elements as other formulas.
No, similar formulas are there. We don't need to worry about like exactly what the formulas are there for different species. You can say that this was the Balmer formula. It predicts this constant will be given to you, and you can predict the Balmer series of lines that appear. Okay.
Okay.
Uh, for hydrogen, though, it will definitely work. It might even work because here you have a z square term actually. It will work for other types of elements also. Okay. The
Uh,
point that I'm trying to say is that there was no explanation. They just got the formula by fluke or by looking at it carefully through the numbers, right?
okay.
But now, once Bohr's model was there, we know now that the energy of every level is minus 13.6 eV z square by n square, right?
Hmm.
So if an electron is going from n is equal to 3 and it is going to a lower energy level like n is equal to 1, right?
Uh,
Suppose the electron was in an excited state, it was at n is equal to 3 shell, right? And then it lost some of its energy and went to the n is equal to 1 level, right?
uh,
Then the gap in energy between these two will give the wavelength of light that comes out, right?
yeah.
The energy loss that was happening here from higher energy to lower energy, that energy is what appears as comes out as the wavelength of light,
Hmm.
comes out as the photon with a particular wavelength. Now, because the energy levels had fixed values, it is not random. Energy levels or not, any energy level is not allowed, right?
Uh,
For hydrogen, the energy levels start from minus 13.6 eV, then minus 13.6 by 4, then minus 13.6 by 9, and so on, right?
yeah.
For helium, it will be minus 13.6 into 4 by 1, then into 4 by 4, then into 4 by 9, and so on, right?
Yeah.
So energy levels are always having fixed values in every atom, correct?
Yeah.
So the difference in energy levels will also be fixed no, all the time.
Hmm.
So because the difference in energy levels is fixed, that's why you always get a fixed wavelength, right?
Yeah.
So when you take the difference, you will get Hc by lambda should be minus 13.6 eV z square by n square minus 13.6 eV z square by n square, right?
Uh,
So you will get a term which looks like 1 by n square minus 1 by n square, right?
yeah.
And you can take this Hc and divide it here, and you'll get something like 1 by lambda is equal to minus 13.6 eV z square by hc multiplied by 1 by n square minus 1 by m square, right?
Hmm.
This formula is what was accidentally discovered earlier, right?
Ah.
So this formula was already known. Now we know an explanation. So that is very good news. That confirms that there is something that is right about Bohr's model, right?
Yeah.
So that was one major success. But again, there were many drawbacks also. First of all, the formula didn't work when there are more than one electron. Like the formula got you close, but not exact. Exact values were not coming. Do you understand what I'm saying?
Ah.
You got somewhere in the neighborhood, but the exact value of the wavelength was not correct. Do you understand?
Hmm. Yeah.
The reason it was not working is because in Bohr's model, conceptually, we considered the attractive force between the nucleus and the electron, right?
Hmm.
We said that this attractive force was mv square by r, right?
Yeah.
Correct? But if you have a multi-electron atom, let's say you have multiple electrons, then there is a repulsive force also, right?
Yeah.
Like the electron-electron repulsion is also there, no, between the electrons.
Yeah.
There are forces here also, and Bohr's model is completely ignoring those forces, right?
Yeah.
So obviously there will be issues when you go to bigger atoms with more electrons, you will not get exact answers, correct?
Hmm. Yeah.
So that was one problem, that it was failing for multi-electron atoms. The next problem was, even when you closely observed the lines in the emission spectrum, for example, let's say we got a line for 456 nanometer in sodium spectrum, then 612 nanometer, then 700 nanometer. I'm just making up these numbers, okay?
Okay.
Let's say these wavelengths were present in the emission spectrum of sodium, right?
Ah.
When people did measurements with more precise instruments, they realized that actually this 456 nanometer line is not actually 456 nanometer a single line. If you looked closely, it was two lines of 455.8 and 456.1.
Yeah.
Do you understand? So this is called the fine structure of the spectrum, fine structure. Basically, several times people discovered that what looked like one line from the naked eye was actually multiple lines here. These wavelengths are quite close and there could be multiple wavelengths which are very close to 612. Okay.
Hmm. Okay.
So the lines were double lines or triple lines and all, which there was no explanation for that in Bohr's model. Okay.
Okay.
Because Bohr's model is saying that energy levels are okay, one energy level n is equal to 1, then another energy level n is equal to 2 and all, right?
So was it not like precise enough?
No, you have to see conceptually what is Bohr's model saying. When n is different, the energy levels are different, right?
Yeah.
What did we do? We did kz e square by r square is equal to mv square by r, right? And we
Uh-huh.
said mvr is nh by 2 pi. And it is this n that determines which shell you are in, right?
Yeah.
That is what is Bohr's model. So only one value n determines where you are, right? Which energy level. Correct?
Yeah. Uh,
But the problem was that actually reality was much more complicated. The reality was that this might be fine, but here only there are multiple energy levels because
oh,
it is
oh.
not n is just one thing. Actually, it is n and l that totally determine the orbital.
Yeah, principal contours and the
So actually, you will say 2s and there is 2p also, right? Or different types of orbitals, right?
yeah.
Both of them are in the n is equal to 2 shell only, right? But the
Hmm.
energy of 2s is less than the energy of 2p, right?
Yeah.
This is the reality. The reality is much more complicated than what Bohr had thought. When you go to the third shell, actually there is 3s orbital, 3p orbital, and 3d orbitals also, right? So
Yeah.
what Bohr had assumed was a single energy level. There were several similar but different energies here, right?
Hmm.
Do you understand?
Yeah.
So obviously now an electron could come from 3p down to 2s. That will be different from a 3d to 2s, right?
3p to 2s lesser energy would be.
So it will not be very different, but it will be similar ballpark, but slightly different, right?
Uh,
So you should get multiple lines which are close to each other.
hmm.
Do you
But in
understand?
Bohr, but in Bohr's model, you just get
Uh,
them as one.
Bohr's model, he didn't even think of these suborbitals and all, right? Other quantum numbers. He was just assuming n is equal to 1, n is equal to 2, n is equal to 3, right?
Yeah.
So therefore, it was incomplete. So again, this is something cannot be explained by Bohr's model. It's not because it was imprecise measurement or something, right? It's a conceptual issue.
अच्छा, okay.
समझ में आ रहा है क्या बोल रहा हूँ?
हाँ.
It's because he didn't even think that there could be more energy levels inside one, right?
Hmm. Got it.
So ultimately, there were many such problems that were discovered. And then we start coming towards the final model, which is the quantum mechanical model of the atom. But before we do that, you have to learn about something known as this Heisenberg's uncertainty principle.
Hmm.
What is this?
The delta x into the delta p
Hmm.
is be greater than or equal to h by 4 pi.
What is this delta x and delta p stuff?
Uh, Delta x is the like position or like the displacement of the thing, and the p is the momentum of it.
But what do you mean delta? You could
Change,
have written x and p, right?
like change in the position of the thing in a given like period.
No, it's not like that. So you have some conceptual issue. That means delta x is not change in position and all. It's actually this word, uncertainty. Uncertainty in the position, and this means uncertainty in the momentum. Do you understand what is the meaning of momentum and uncertainty word?
We are not certain about it.
So uncertainty means the error that is possible in your measurements, right? Error. Like suppose you had an instrument which is a weighing scale and you measured the weight of some object to be 2.1 kgs, right?
Hmm.
So if you think about it, that weighing scale will have something called a least count, right?
Yeah.
Least count is the smallest thing that can be accurately measured from that scale, right? Smallest weight,
Yeah.
correct? So
Hmm.
if the least count of that instrument is 0.1 kg, then all you can say is 2.1 or 2.2 or 2.0, right?
Yeah.
Do you understand what I'm saying?
Huh.
But if it is a highly sensitive instrument, you might be able to say 2.135 kg, right?
Hmm.
This instrument is going down to 0.001 kg. That is the smallest thing it can measure, right?
Yeah.
This instrument is only going down to zero point 0.1 kg, which is like 100 grams, right?
Huh.
So if you measure from this instrument, the uncertainty in your measurement is 100 grams, right?
Hmm.
Because no matter what you are saying, 2.1, it could be actually 2.199, right?
Yeah.
Right? Or it could be 2.2 or something. Do you understand what I'm saying right now?
Yeah. Yeah.
The uncertainty here is 100 grams because that is the smallest thing that can be accurately measured, right? The
Yeah.
uncertainty here is 1 grams, right?
Hmm.
Correct.
Yeah.
So similarly, when I say delta x, I mean what is the uncertainty in the position? So electrons and everything are super tiny. So actually you can't really see them, no?
Yeah.
Nobody can actually see an electron. So what people are doing are trying to measure its position or velocities through some indirect ways, right? So
Mm.
if you are doing whatever kind of measurement and you are saying there is some uncertainty in the position, that means how much you are wrong by, how much could you be wrong by, right? Do you understand what I'm saying?
Yeah.
So you might be knowing the position up to, like, position might be wrong by 2 nanometer. Maybe 2 nanometer is the uncertainty. We don't know whether that much precise or not, right? So basically you can measure the position with respect to this origin and say it is at 9.1 nanometer from the center plus minus 2 nanometer. Do you understand what I'm saying?
Yeah.
That means this much you are not sure of, right?
That is what you're uncertain.
That is what we are talking about delta x here. Okay. And when we are saying delta p again, you can measure the momentum of the electron, but there will be some plus minus some unknown point, right? Some error,
Yeah.
which we are not sure about because it's all experimental, right? So
Hmm.
that is what is the uncertainty in momentum. Okay.
Okay.
So what Heisenberg's uncertainty principle is saying is that the uncertainty in position and momentum is always greater than equal to h by 4 pi. Okay. Now you should know that the value of h is quite small. It is Planck's constant. The value is like this, right?
Yeah.
So the product of the two uncertainties is greater than this very small value, right? Correct.
Hmm.
Now think about the consequence of that. Let's say you have delta x into delta p is greater than equal to h by 4 pi. What this means, this equation, is if by some miracle you are able to reduce the uncertainty in position to be very close to zero almost. Do you understand what I'm saying?
Ah.
This is also not close enough. Suppose you have gone really down and almost zero uncertainty, right? Correct?
Okay. Okay.
Then what will happen to the delta p?
It'll blow up.
Hmm. It will become almost infinite uncertainty, right?
Yeah.
So that is a very big paradox that you cannot really measure both of these quantities accurately at the same time, right?
Hmm.
Basically, it's saying that if you try to know the position of an electron properly, then the momentum will be totally unknown, right?
Yeah.
If you
Ah.
try to know the velocity very properly, then the position will be totally unknown. Do you understand?
Yeah.
So this principle was derived by Heisenberg, and this totally destroys Bohr model. Why do you think it destroys Bohr model? Bohr model is cancelled after this.
Hello.
Hello? Can you hear me?
Hello.
Hello?
Yeah. Sorry, my internet went.
So what I'm saying is, once uncertainty principle was discovered, it totally destroys the Bohr model. Okay.
Because in Bohr we knew both location and the momentum.
In Bohr's model, as soon as you had the idea of an orbit, if you are placing an electron in an orbit, you are already fixing its position, right?
Yeah.
If you have fixed its position, the velocity should be totally unknown, right?
Hmm.
But in Bohr's model, we are pretending like we know the velocity and radius, everything, right?
Ah.
So that is not actually the accurate description. Bohr model is able to predict some results that's happening because of fluke. It's almost like a fluke thing is happening because of which it is successfully predicting some results. But the reality is very different. It is not at all moving around in orbits like this. Okay.
Yeah.
So now there is another thing that you need to know here, which is called de Broglie wavelength. De Broglie wavelength or something known as matter waves. So basically the point is that electrons behave not like pure matter particles, they also have wave-like properties. Okay? Particles also have wave-like properties. Have you heard of this de Broglie wavelength concept before?
Yeah. Um,
Hmm.
I
So
forgot the formula though.
that's fine. But the idea you need to remember, what is the idea? Okay. So what this means is that any particle, see, there is a very big difference between a particle and a wave, right?
Yeah.
Like a particle is localized, it's only here, right? But a wave is sort of distributed.
Hmm.
Do you understand what I'm saying?
Yeah.
Like you cannot say that this wave is located at one point. Actually, it is spread over this whole wavelength, right?
Uh,
This wave is going to be from here to here. That is the wave, right? But when you talk about a particle, it is localized, right? Correct?
yeah.
Now, the energy and all of a particle, we usually do kinetic energy of a particle and so on. For a wave, the energy will depend on its frequency and wavelength and things like that, right?
Uh,
It might also depend on the amplitude of the vibration and stuff, right? So
yeah, it does.
technically, when we talk about light, for example, light can show both types of behavior. It can be like a photon, a particle, and sometimes it can behave like a wave. So there was a huge controversy for hundreds of years where people were figuring out, okay, what is the behavior of light? So first Newton thought that it behaves like particles because he saw that light was going in straight lines, right? So
Hmm.
Newton's idea was that light is going in straight lines, so therefore it must be like a particle. But then after that, there was Thomas Young, and he figured out so many experiments like Young's double slit experiment and so on, where people saw that it was showing wave-like behavior. You cannot explain it with particle behavior.
Hmm.
Things like interference and superposition of waves were happening, right?
Uh,
You have heard of these things or no?
I have.
So there are many experiments where light was behaving like waves. For 200 years, people kept seeing this wave-like behavior of light. And by 1800 or 1900, everyone believed that Newton was wrong and light behaves like waves, right? But then came another experiment, which is the photoelectric effect. And then again, wave theory was not working there. You cannot explain photoelectric effect with wave theory. And Einstein said that, okay, it is the photon theory that will work here. So light is again behaving like particles now. Do you understand what I'm saying?
Yeah.
So there were a lot of different experiments which gave different conclusions. And finally, people realized that actually, just like light, all matter has this dual behavior. Dual behavior means it can show wave-like behavior sometimes, it can also show particle-like behavior sometimes. And what happens depends on the experiment that you are doing. Depending on the experiment, sometimes you will see particle-like behavior or wave-like behavior. Okay. The
Hmm.
actual theory of it is slightly advanced. You will have to write a wave function, and then you will be able to show how the wave function collapses at certain moments and it becomes a particle-like behavior. But we don't need to concern ourselves with that. For now, just know that both types of behavior are possible for light and also for other matter particles.
Hmm.
Okay. Depends on the experiment what properties will come out and what will feel like the right explanation. Basically, what you need to realize is that the word wave or the word particle is a artifact of our English language. We have made those words, right?
Yeah.
And we have given some meaning to the word wave and some meaning to the word particle, right?
Hmm.
Nature doesn't care what we are calling it. Like the universe doesn't care whether humans can understand it properly or not. Like they are not going to bother about us. So our language is not sufficient, or our language doesn't have a word for what is actually going on in nature. Do you understand?
Yeah.
So actual behavior is quantum mechanical and it is complicated. What we have so far understood is two totally different sounding concepts of waves and particles, and that's why people are confused about it. You
Hmm.
understand?
Yeah.
Because in common real life situations, we always encounter particles and waves as something totally different, right?
Hmm. Yeah.
But in this subatomic world, it is actually totally linked, and it is something, a combination of both of these, that is the reality, which we are finding it difficult to describe. Do you understand
Hmm.
what I'm saying?
Yeah.
So don't worry about that so much, but just remember that any particle has a de Broglie wavelength. You can describe it using a wave also. And the wavelength is basically given by h by mv. Okay. So basically you can say de Broglie wavelength of a particle is h by the momentum, right?
Yeah.
Now think about it. If you have a real life particle of the order of particles that we see in our life, m and v momentum will be much bigger than this h, right? Because
Yeah.
h is
Mass is
Planck's
bigger.
constant and it is almost 10 power minus 34, right?
Huh.
Whatever real life particle that we will see in our lifetime, we will always have m and v will be much higher, right?
Yeah. So the wavelength will also be very less.
So wavelength, when you do for normal particles, it's almost zero only. There's nothing to worry, right?
Hmm.
Correct.
Yeah.
But if you do that calculation for a subatomic particle like an electron, let's see what happens. Lambda is equal to h by mv, but this time we'll do it for an electron. Okay. 6.6 into 10 power minus 34 divided by mass of an electron is 9.1 into 10 power minus 31. And let's say the electron has the speed of the n is equal to 1 Bohr's model hydrogen electron, right?
Okay.
So it will be
So,
roughly like this, no? 10 power 6 into 1 by
uh,
1, right?
yeah.
In SI units, this is the rough speed of a Bohr's model hydrogen electron, right?
Hmm.
Let's see what is coming as the lambda for that electron. So now see, it is almost 6 by 18. So let's say 1 by 3 and multiplied by 10 power minus 3, 10 power minus 9,
Yeah.
correct?
Hmm.
Now think about it. This is 3.3 angstrom, right?
Yeah. Huh.
Now imagine that the wavelength of the electron is coming out to be 3.3 angstrom, and in a hydrogen atom, the nucleus was like this, and the radius of this orbit was 0.529 angstrom, right?
Hmm.
Do you see the problem now?
Yeah.
The electron's wavelength, the electron which we thought was a point particle, it is actually a wave with a wavelength of 3.3 electron angstrom, right? Correct?
Hmm. But then it's going around, right? So,
So understand that if you are representing the electron as a wave, it will have a wavelength of this much, right? Roughly.
yeah.
This wavelength is bigger than the size of the atom only.
Hmm.
This is half angstrom, okay? A hydrogen atom's radius is half angstrom, right?
Yeah.
The wavelength itself is bigger than that. Like what this tells us is that you don't even know where the electron is, no?
Huh.
Like unless you draw the full wavelength, you cannot really say that that is my electron, right?
One.
Like what I'm saying is the electron here, if you represent it as a wave, it will be delocalized over this much distance, right?
Yeah.
You can't
Yeah.
really say that the electron is here. You have to say the whole thing, right?
The whole wave.
Whole wave will be the electron, no, not some small part of it. So if the
So,
whole wave is an electron, the hydrogen atom size is much smaller than that, no?
Yeah.
Basically, the size of hydrogen atom is much smaller, which means that the reality of how the electron is in an hydrogen atom is much more complicated. It's not like an orbit or something. Because
Hmm.
technically, the electron is the uncertainty in position of electron will be bigger than the atom size, right?
Yeah.
So that basically tells us that the normal standard understanding is wrong. Okay. And now we have to come up with some new models, which is the quantum mechanical model, right? So, because actually here when we were doing particle model, it was feeling like hydrogen, it was nicely orbiting and all. But now that is totally wrong. We don't even know where the electron is. Maybe it is going around the atom like this, right? In multiple, in a long wave, right?
Yeah.
But we don't know where it is or how it is because the size or the wavelength, de Broglie wavelength of electron is so big compared to the hydrogen atom size.
Yeah.
Correct?
Yeah.
So that sort of like confirms that this uncertainty principle is definitely correct because if you try to be certain of the particle's position, you can't really be certain. No, the whole way atoms is only the size is so small compared to the wavelength of the electron.
Um,
You can't pinpoint that the electron is here, right? Because
yeah.
the wave of the electron is bigger than the atom itself.
Yeah.
The atom could be anywhere, the electron could be anywhere, right?
Yeah.
So now what we will do is we'll try to understand the next step, which is the quantum mechanical model. You should go through the theory a little bit, see what they are saying about Schrodinger's equation and all. I have sent you the other book, right? Chapter 5, where you were supposed to read, right?
Yeah. Yeah. You said it.
So that chapter 5, should read the quantum mechanical part, the part that is towards the end of the chapter. Okay.
Okay.
And we will discuss what we have to understand from there, and we'll continue from this point.
All right.
Okay.
And so tomorrow also I have half day.
Hmm. So what
So
time will you be free?
I'll be back by 1 o'clock. So anytime after.
Okay, I'll tell you the time and we can confirm it and then do it.
Okay, fine.
Okay, fine. That's all for now then.
Thank you, sir. Bye.
Bye.